So now we will start with the non-linear amplifier. So the OPAMP part 2 for the non-linear amplifier. Okay, so for this one, okay, it's a little bit different from the linear amplifier. So, but we only have two types for non-linear amplifier. Okay, non-linear amplifier, which is a voltage comparator and also Smith trigger. Okay, only these two types will be asked in the final exam. So this question for the non-linear amplifier will be your number 4th question. Okay, your final exam gonna have 4 questions. So first question 1 is MOSFET. Second question is multi-stage amplifier. Third question, linear amplifier, what we have done in the last week. Fourth question on the non-linear amplifier. Okay. Right. So for the non-linear amplifier, okay, so for the non-linear amplifier, first type is comparator. So comparator has 2 inputs and 1 output. I think all of you know for the linear amplifier last time also we have 2 inputs and 1 output. So the operation basically is to compare. What is the input? Okay, so the op-amp will compare, okay, between the negative input and positive input. Okay, so op-amp will do his work and make comparison. So there will be what we call it as a specification. So that will be the output. Okay, so the output swings between its maximum and minimum voltage. Okay, depending upon the V in. Okay, is greater than the V reference. Okay, in this case, so this is your op-amp. Negative input V minus. Okay, if you still remember, and positive input V plus. Okay, so this plus minus, so this is the what we can say as the voltage supply of the op-amp. So this is the maximum voltage output that can be reached by the output if the supply voltage is 15 and minus 15 volt. So whatever the input here, the output cannot be greater than the input supply here. Okay, plus minus 15 volt, for example. Okay, like in here, so the output is always a square waveform. Okay, like this. So for example, your input is square waveform. If let's say it is 10 sine omega t. Okay, so this is the input 10 sine omega t. So this is the reference voltage. So there is some condition, okay, need to be to satisfy the op-amp, and you will get the limit. Okay, so for example, up to the positive cycle, the input will be saturated at V plus saturation, and the negative cycle will be saturated at negative saturation. So this is just the example lah, for example. Okay, so the output must be always in square. So the maximum is at positive saturation, which is 10 volt. The negative cycle will be negative saturation, which is negative 10 volt. Okay, so this is the op-amp. So it has 2 input. Okay, so one input will be the input voltage that applied to the op-amp. For example, 10 sine omega t or 15 sine omega t. That's all. Okay, so reference. Okay, reference voltage is where your circuit will be connected to all resistor. Okay, so this will be your reference. Okay, so the V out here is equal to the gain times V in minus V reference, or the difference of input. Okay, same like in the linear amplifier. Okay, if V input greater than the V reference, so V out equal to the positive infinity. Okay, so this one, but practically it will hit the positive VCC. So this is actually the condition, okay, for the comparator. Okay, so this is the condition for comparator. If V in, okay, greater than the V reference, so the V out will be equal to the positive VCC. Okay, if V in less than the V reference, okay, so V out will be negative, infinity. Wait, okay, negative infinity and equal to negative VEE. So the application is one of the application that use comparator OPAMP. Okay, OPAMP as comparator is detection of QRS complex in ECG. So ECG is a medical health the medical health equipment. So for example, it has this input. Okay, your heart rate is this is the heart rate of a person. So what is the if their heart rate reach the V reference, so the output is of heart rate equal to 1. If it doesn't reach the V reference, so the heart rate is equal to 0. So we get a digital quantization of the output instead of in this kind of noise term. Okay. So this is where the condition is. Okay, so the top figures is actually showing the open loop operation of the voltage comparator. So where it has, so A is the gain. Okay, V out is gain times the difference of the input voltage. Okay, and the below is the transfer characteristic of the voltage comparator. So when V plus greater than the V minus, so output is at maximum. So this is the first condition. Okay. Okay. So this is the condition of the OPAMP comparator. Okay. So if the input, okay, this input referring to this input V plus, okay, greater than the V minus, okay, so what will be the output? Okay, the output is equal to the V plus saturation. Okay, the output will be equal to V plus saturation. If you can see here, so so this is the V plus saturation or V out saturation. Okay. Wait. Mm, mm, mm. Okay. So this is the negative V out saturation. Okay. So the second condition, if the input V minus, okay, this V minus, okay, greater than the V plus, okay, whatever the input is, you have to find out. So this is just the condition lah. So this is the condition. Oh my God. So this is the condition of comparator. Okay, so if the input V minus greater than the V plus, therefore V out is equal to the negative V out saturation. Okay, we will look at the example, but to solve comparator question, so we need to apply this condition. Okay, so remember, so only these two conditions that will be applied in this non-linear op-amp. Easy. Okay. So for practical transfer characteristics, so this is so this basically shows the what is actually happening. So this is ideal. Okay, so when V plus greater than the V minus, so you will get exact V out saturation. Okay, like this. Okay, a straight line like this. Okay, but when your V minus greater than the V plus, so you will get exact V out at negative like this. Okay, so this is for the ideal case. Okay, but in practical, by assuming the delay of the op-amp, by assuming the voltage supply of the op-amp, the noises and everything, so this is what happened. Okay, instead of it reach at this point, okay, there is a delay where it reach the V out saturation at this point. Okay, so as here the negative, okay, instead of it reach at this point, so it has delay where it reached the saturation at that point. So the practical transfer characteristics more look like this. Okay, so this is for the ideal case. Okay, for the ideal case. All right, so let's take a look on the example. So this is one of the example. So I want to copy first this. Okay. All right. Hold on. Okay. So I copy that. Okay. So this is a question. So the question give the circuit like that. Okay, where you have this circuit. Okay. So this is your comparator. So your comparator 7-form wide comparator. Okay, the V minus. Okay. So this is the V minus. Let me take my pen out. Okay, so this is the V minus, this is the V plus. So V minus now is connected to the resistor and to the voltage supply. So the maximum voltage supply here is 12 volt minus 12 volt. Okay, so this is the circuit of the comparator. Okay, so your job is to find to solve this circuit. Okay, so the first question asks you determine the V reference. So now where is the V reference? Okay, so like here, only we have one output. Okay, and then we have one V referent and one V in. Okay, so in this case, okay, one V in. So in this case, your V in is at V plus. Okay, this is your V in. So now your V reference will be only left V minus. So this is your V reference. Okay, so this is your V reference. Okay, so determine V reference. Okay, one thing determine the V reference. Okay, now let's determine. Okay, let's go step by step. Okay, so determine the V reference. So what will be your V reference in here? Why my pen like that? Okay, all right. Okay, so how to determine the V reference? So this is your V reference. How to determine? Anyone? You got an idea? So at this point is your V reference. Okay, at this red dot here. So V reference is equal to, how you solve the V reference? How to find V reference?
V Thevenin.
Correct.
Thevenin.
Yes, V Thevenin or voltage divider, right? Okay, so same like voltage divider, V Thevenin, your friend is right. Therefore, V reference is equal to the 10K over 10K plus 10K times 12 volt. Okay, so this one will be 6 volt. Okay, 6 volt. Okay, so this is your V reference. Okay, 6 volt. All right, so now, all right, in this case, so this, the only condition that you need to do is by doing this. Okay, so this condition where input V plus greater than the V minus, then V out equal to the positive V out saturation, and V input V minus greater than the V plus, then V out equal to the negative V out saturation. All right. So in this case, okay, in this case, your V minus is V reference. Okay, your V minus is V reference. Okay, while V plus is V in. So the question asks you when V in equal to the 2 volt is diode on or off, and V in equal to the 10 volt is diode on or off. So now you need to find your V out first. Okay, what is your V out? Okay, in order to determine whether the diode on or off, you need to find your V out. Okay, so let's clearly look here. So in this case, your V minus is equal to the V reference, and the V plus is equal to the V in. All right, so this is your condition. Okay, this is your condition. Okay, um, condition for this circuit. Okay, so in order to determine whether it V out equal to what, then you have to apply this table. Okay, this one where I highlight here, the star, put star here. So now if I so let me write again. So V minus equal to the V reference, and V plus equal to the V in. Okay, what is your V in? So let's take an example for V in 2 volt. Okay, what is the V out? All right, so let's take a look here. Okay, so for this case, okay, by applying this condition, so in this case, is it okay, V plus greater than the V minus, or V minus? Oh, sorry, I'm using a different tablet today, not my. Or V minus greater than the V plus. Which one? Okay, now V reference is 6 volt. Okay, your V in this case 2 volt. Therefore, which one? Is it V plus greater than the V minus, or V minus greater than the V plus? So your V reference is V negative, which is here 6 volt. Okay, so your V plus, which is your input, so this is your input, okay, V input, which is 2 volt. So which condition is correct here? The left one or the right one?
Right one.
Correct. Okay, so the right one. So this is the wrong condition. So if we take the right condition, which is V minus greater than the V plus, what will be your V out? Look at this table.
Negative VR saturation.
Negative V out saturation. Okay, negative V out saturation. Okay, so for negative V out saturation, so what is the V out saturation? So look at the circuit here. So the V out saturation is the power supply of the op-amp, which is how much? This value is the power supply. This is the maximum point saturation. So in this case, it is equal to negative 12 volt. Okay, negative 12 volt. All right, did you get the point here, everyone? All right, so now, okay, not yet finished the question. They said that if V in equal to volt, determine whether diode on or off. So now you already have your V out here is negative 12 volt, for example here. Okay, so now if V out negative 12 volt, negative connected to the anode of your diode, okay, this is cathode, what will be the LED looks like? So if I draw it here, so what happened to your LED? Okay, so this is negative plus 12 volt, and this is for 70 ohm, and this is your LED. So now the current is in different direction, where negative connected to the anode of the LED. Therefore, LED will be forward bias or reverse bias.
Reverse
Okay.
bias.
Yes, LED will be in reverse bias. Okay. Therefore, when LED reverse bias, is it on or off?
Off.
Off. Yes. Off. Yes. Okay. So yeah, so this is partial question. I simply took partial question in the example because you can see the real happens, what is actually happen in comparator. Okay, so it is easy. Okay, why? You only took this table. Okay, only this table. Okay, only this condition. Okay, need to be okay, you need to fill up this condition, okay, in order to solve the question. All right, so let's take a look for this one. V in 2 volt. Okay, for example, the second one for V in 10 volt now. Okay, so V in 10 volt is the diode on or off, so you need to find your V out first. Okay. Okay, so what will be your V out? Okay, so in this case, your V in is your, okay, V in is V plus. Okay, and V reference, which is 6 volt, is equal to the V minus. All right, so now your V in, which is V plus, greater than the 6 volt, right? So your condition now become V plus greater than the V minus. Agree with me?
Yes.
Yes. Okay. So in this case, which is Y 10 volt, okay, greater than the 6 volt. Okay. All right. In this case, you will get your V out is equal to, look at the table above. So V out equal to,
12 volt.
yes, correct, plus V out saturation, which is plus 12 volt. Okay, so when V out plus 12 volt, okay, now this one, okay, become plus 12 volt. Okay, if you cannot imagine, it is straight away you can see that the LED forward bias, but you can always draw like this. Okay, so you have 47 ohm. Okay, and then you have your LED. Oh, what's this? Okay, so you have LED, yeah. Okay, plus minus 12 volt. Okay, so current in this direction, which is go to the anode of your diode. Therefore, LED will become forward
Forward
bias.
bias.
Yes,
On.
so LED will turn on. Okay, so that's it. Okay, so this is, I think we cannot ask you more. Okay, so this is non-inverting op-amp comparator. Can someone tell me why it is non-inverting? Why the this one named as a non-inverting? Because V input connected to the plus. Okay, same like linear op-amp. Okay, when V input connected to the negative, it will be inverted. When V input connected to the V plus, then this is non-inverting. So we expect that the output also not invert lah, means the same as the input. All right, so this is for the case of non-inverting. So we have another example here for inverting. Okay, for inverting. All right, so I want to copy for a while. Okay. Okay, so this example, I think almost a similar example lah, same. So this is this one for part A, okay, in the final exam. This one for part B in the final exam. Okay, so the question, so given the circuit of the inverting comparator, why inverting? Because the input here, the input supply connected to the negative, to the V minus. Okay. Okay, so they ask you, I think the same step, okay, the same step what you have done in here, okay. So you repeat it one more time. Okay, let's do it together. Maybe you still confused about the condition and so on. So let's do it again. All right, so first you need to find the V reference, okay. So in this case, you have V minus connected to the V input. Now your V plus is your V reference at this note. So your V reference is equal to the 10K times 10K plus 10K times 12 volt, okay, which is equal to same, right? 6 volt. Okay, 6 volt. Okay, so the V reference is equal to the 6 volt. Okay. All right, so in this case, so let's just put that the V in is equal to the V minus, and then the V reference is equal to the V plus. Okay, now let's take the condition. So for V in equal to 2 volt. Okay, let's do it again. Okay, so that you will become familiar with the condition. Okay, so when V in equal to 2 volt, okay, when V in equal to 2 volt, diode on or off. Okay, so you know that V in equal to volt, which is equal to the V minus. Okay, in this case, V reference is fixed 6 volt equal to the V plus. So in this case is which one is the condition? Is it the first one or the second one? Which condition?
First, first one.
First, yes, first condition. Okay, so in this case, it is V plus greater than the V minus. Okay, therefore, V out is equal to the V out saturation. Okay, plus V out saturation, which is plus 12 volt. Okay, so you need to do the same thing again, okay, for the condition. So when V out equal to the plus 12 volt, can you all straight away determine the LED forward bias or reverse bias?
Forward bias. Oh,
Yes, forward bias. Okay, forward bias, and LED will on. So this is the answer. Okay. All right. Okay. The second one, okay, for so this is easy actually, but I do it twice lah, tak apa. So that you will be familiar with this condition, okay? So quite confusing, but then if you list out everything, you will be okay, okay? When V out 10 volt, okay, 10 volt, okay. So when V out 10 volt, V out, V in 10 volt, so V in is equal to the V minus, and V reference is your fixed voltage, which is 6 volt equal to the V plus. So this one is actually which condition? Number 1 or number 2? Number 2. Okay, so in this case, V minus greater than the V plus. Okay, therefore V out is equal to the negative V out saturation, okay, which is negative 12 volt. Okay, so in this case, if this point is negative 12 volt, so LED forward bias or reverse bias?
Reverse bias.
In reverse bias. Okay, so LED will, oops. Off. Oh, oh, why? LED off. All right. Okay. Okay, so that's it for this one. All right. So this is example 1. Okay. Oh, I cannot delete this. Why? So become here. It's okay. So this example shows the draw the output waveform. Okay. In order to draw the output waveform, you need to find the V in. The V out, sorry, you need to find the V out. Okay, given the sinusoidal input is Vm, okay, and if V reference equal to 0 and V reference equal to Vm over 2, assume that V out is equal to the plus minus VCC. Okay, all right, so let me copy for a while. I need to copy this first and put it here. Yeah. Okay, so this circuit is simple. Okay, so it has where it doesn't have all the resistor and everything. They just said V in here, V in over here. So this V in, okay, is equal to this one. Okay, this one. So this is the V in. So V in here is actually equal to Vm sine omega t, okay, because this is sinusoidal, okay. So V in is equal to Vm sine omega t. Why Vm? Because the maximum point there is Vm. So just Vm sine omega t. So V reference, so this is the V reference. So this is V minus, so this is V plus. So V reference, you have two, one at 0 volt, the other one at Vm over 2. Okay, so let's take a look here. So let's take a look for the V reference equal to 0. Okay, so for this one, V reference equal to 0 volt. Okay, by using the same condition over here, 1 and 2. Okay, so let's take a look cycle by cycle. Okay, so now previously you have numbers, now you have waveform. Okay, so your V reference is 0 volt. Okay, so V reference 0 volt, where 0 volt? So this is 0 volt. Okay, so this is 0 volt. Okay, so you have the condition. So in this case, your V in is equal to the V minus. Okay, V minus. All right, so V in, so this is actually your V in equal to the V minus. So this is also V minus. This is V minus. Okay, so where is your V plus? So V plus is at V reference. So the whole line here is your V plus. Okay, now to find the V out, okay, you need to cross check with the condition. Okay, let's take a look on the first cycle here. So I highlight it here. Okay, I highlight it here. Okay, so the first cycle there, can someone tell me? So is it V minus greater than the V plus or V plus greater than the V minus? Look at that. So V
V
minus,
minus greater than V plus.
correct, correct. So this is your line of the V plus, V reference. So now all your V minus is above the V reference, therefore V minus greater than the V plus. So if V minus greater than the V plus, look at the table over here. So V out will be equal to what? V out equal to?
plus VCC.
Yes, plus VCT. Okay, left and V plus. So V minus greater than the V plus, therefore V out equal to negative VCC here, okay? Negative V out saturation, which is negative VCC. That's why the output here negative VCC. Okay, all right, the second one, okay, the second one, so let's take a look on this condition pula. Okay, this one, okay, this one, all right. So for this one, all the V minus is below the V reference, as you can see. So V reference is on top, so V minus less than the V plus. Okay, look at the condition there. When V minus less than the V plus, so V out is equal to plus VCC. Okay, that's why you got the line here plus VCC. All right, okay. And so on. I think for the rest, cycle will be the same. Okay, so you got it here. So this is your output waveform. Okay, so this is the answer for the output waveform. Okay, sometimes they ask you to calculate the V out or they want value. Sometimes they ask you to draw the waveform. Okay, if they ask you to draw the waveform, definitely they will give the input in terms of waveform. Okay, like this, where the input equal to Vm sinusoidal. So your output must be also in the waveform. But every time comparator, no matter what the input is, sinusoidal or what, the output must be in square waveform. All right, so the left one is for the Vm over 2. Okay, you have to apply the same concept. Okay, the same concept for this one. V reference is equal to the Vm over 2. Okay, so now V reference is equal to the Vm over 2. Okay, you need to do the same thing. So this is your V reference. Okay, so this is your V minus. V minus, V minus. Now this is your V plus, V plus. Okay, you need to apply the same condition. Okay, the same condition happens. Okay, so now instead of you have 3, so you have, as you can see here, you have this one. Okay, this one. Okay, and also this one, and also this one, and then this one. Okay, and then this one and this one. Okay, means that you need to do 1, 2, 3, 4. Okay, the other policy cycle is the same. So if you apply the same method, you will get like this. The output, here is the output for this part, here is the output for this part. Okay, you can check, you can try again and check your answer. Can you all do this on your own?
Yes.
All right, great. Okay, so comparator has problem with noises, of course. Okay, please try. Okay, so comparator has a problem with noises because usually used in the ECG, in the heart rate monitoring system, basically in medical equipment. Okay, so if the input V in is superimposed with noise, okay, this will cause a false triggering. Okay, one way to overcome this issue is another type of nonlinear amplifier, nonlinear op-amp, which is made trigger. Okay, so when you have this kind of noise, okay, so this noise like this, okay, so okay, so when you have this kind of noises, so you have this noise like this. Okay, so how to trigger too many noises, like means too many condition. So you can you can see from here you have many lines here. Okay, like for example here you only have 1 lines, 2 lines, 3 lines, like that, right? So here you have many condition. 1, 2 is noises and ups and downs, so not stable. So how to solve this issue with the input that has many noises is the Smith trigger. So what is Smith trigger? So Smith trigger, the circuit looks same like the comparator. Okay, almost same. Okay, but this one, the Smith trigger has positive feedback. Okay, if you can see here, for the comparator, okay, if the you might cannot differentiate, okay, between the circuit of comparator and also circuit for Smith trigger. So how you differentiate it is, for comparator, it doesn't have feedback, means from output to the input, no resistor, either at negative or at positive. They're not connected to each other. So we define V out based on this condition. Okay, this condition, right? But for the Smith trigger, okay, so this is one example. As you can see, no connection between, no resistor between output and input, means no feedback resistor. Okay, in this example as well. So this is comparator. But for Smith trigger, it has positive feedback. It has feedback output to the input. Means this resistor R2 is the feedback resistor where it connect between input and output. Okay, so this is Smith trigger. Okay, so for the Smith trigger, comparator, same like, so we apply the same condition with the comparator just now, the same condition. So I need to copy, sorry, give me, I need to copy just the condition just now. So this is condition with, put it here and maybe here. All right. Okay, so this is the circuit, okay, where it has, so in here you also have V reference. Okay, so as you can see from here, so this is V minus, which is connected to your V input. Okay, and you also have V plus, which is connected to your V reference. So this is your V reference. So you need to find this V reference. So what is the V reference? So V reference is equal to the 2 voltage divider. Okay, so, oh, sorry. So not the V reference. So it has V reference over there. Sorry. So it has, so this point is V plus, just let it be as V plus, and this is V reference. Okay, so to find the V plus, you have to do 2 voltage divider. Okay, so this V plus, if you still remember how to solve it, so V plus at this point, you have, since you have 2 voltage, okay, at the V reference and also this point V out, okay, therefore you have 1 here plus this one here. Okay, 2. Okay, so V plus is equal to the V reference times the opposite resistor, which is R2, over R1 plus R2, plus V out, the opposite resistor is R1, okay, over R1 plus R2. So this is voltage divider, which is the same like you have learned in the electrical circuit analysis, but with 2 power supply. So this voltage divider, this one voltage divider is 1 power supply. Okay, when you have 2 power supply, then you have another portion here. Okay, so that is for 2 power supply. Why 2 power supply? Because 1 power supply is V reference, the other one is V out. Okay, in order to find it using voltage divider rule. Okay, so V plus equal to the V reference, the opposite resistor R2 over R1 plus R2 and so on. Okay, so this condition, I think the same condition like in the table below. So when V in less than the V plus, V out equal to the V out saturation. Why it said so? Because V in is actually the V minus. So it is actually what the statement mean, V minus less than the V plus. So look at the table here. So it is the first condition. Okay, so V in less than the V plus equal to the V out saturation. So this is what it meant by the condition. Okay, so in this case, okay, this is your equation, the voltage divider equation for the V plus. Okay, so you have to apply, you have to replace this V out. Okay, in Smith trigger, you have two possibility of V out. Okay, one possibility when this V out equal to the positive saturation, okay, or the other possibility, it is equal to the negative V saturation. Okay, so V plus, okay, we take the first one, okay, when, okay, V out equal to the V plus saturation. As you can see, this V out now is being replaced with plus, okay, plus V out saturation. So whatever the value here, it is equal to the V upper trigger, okay, upper trigger voltage, VUTP, okay. Again, I repeat, so this is the general equation of the voltage divider rule for the V plus, okay. So you need the V out in Smith trigger can be two possibility. It's either your V out equal to the V plus saturation, or it's either your V out equal to the negative V saturation. When V out equal to, oh, sorry. Okay, when V out equal to the V plus saturation, therefore, this one will be equal to VUTP. Okay, so the other condition, all right, in this case, so when V in is increased, so if you look at here, V in is increased up to here, okay, this is your V in. Okay, the V out is equal to the V out saturation plus, okay, plus, all right, so stay at this value until V in reach VUTP until here. Okay, but beyond this point, V in will still keep increasing. Okay, V in will still keep increasing. Okay, larger than the VUTP. After that, it will be changed to negative V out saturation. So this is what happened for the V upper trigger. Okay, V upper trigger. All right. So, like I said just now, so V out can be positive V saturation. And what happened when we take V out equal to the negative V saturation? So this one, as you can see, so V out here equal to the negative V saturation. When V out, oh, V out equal to negative V saturation. Okay, so this one, okay, negative, if you can see here negative, okay, this is negative. So the output will be, the V plus now will be VLTP, which is voltage lower trigger, okay, lower trigger voltage, BLTP, okay. So this is for this condition, okay, for this condition, okay. So when V out equal to the VLTP, okay, the negative V out equal to the negative V saturation and stays as long as V in greater than the VLTP. Okay, and if the V in is reduced to V in equal to the VLTP, it will keep reducing until V in less than VLTP. So the overall VUTP and VLTP, V out versus V in will looks like this. Okay, so this is when your V out, okay, so V in, for the case of VUTP, like this, okay. So this is what happened when your V out is equal to the VLTP, right? So this is what happened for the transfer characteristic. So this is the transfer characteristic for your Smith trigger. So the drawing is the same, okay, just like that, where you have V out saturation. Okay, this is your V out saturation, negative V out saturation, which is fixed value. The only thing you need to find is VUTP and VLTP. Okay. So, but the drawing is fixed like this, okay, where you have point VUTP and then you have point VLTP. All right, so for the hysteresis, what is hysteresis? It is actually a property that means the device behaves differently when its input is increasing from the way it behaves when its input is decreasing. Okay, in other words, okay, the output will still switch when the input increases to one level, but will not switch back to its input fall below the different level. Okay, so it is a desirable characteristic because it prevents the comparator from switching back and forth in response random. But you can calculate the V hysteresis. Okay, so hysteresis voltage VH of Smith trigger is given by this equation, which is equal to the VUTP minus VLTP. All right, just this one, whatever the value you got for the VLTP and VUTP. All right, so this is one of the example. Okay, so let's take a look the example here. All right, first thing is to find the VUTP and VLTP. So you have the main equation there where V plus equal to the V reference R2 over R1 plus R2 and plus V out R1 over R1 plus R2. In order to find VUTP, that V out, so this V out, right, this V out will be replaced with positive V saturation, this one. In order to find VLTP, this V out will be replaced with negative V saturation. Okay, so let's take a look here. All right, so the same circuit. So in order to find this, so this is V minus, so this is V plus, okay. This is actually V, so let's write down the equation. So V plus is equal to let's take a look over here. It is equal to the R1 plus R2 times V out plus R2 over R1 plus R2 times V reference. Okay. Oh, terbalik lah my equation, but doesn't matter. But no, it's matter. So let me write again. Okay, so it is R2 over R1 plus R2, V reference, plus R1 over R1 plus R2, V out. Okay, so where is R1, where is R2? So R1 connected to V reference, R2 is the feedback. Okay, so this is R1, so this is R2. All right. Okay. So VUTP is when you replace this one, this V out, with positive V saturation, which is plus 10 volt. Okay. So you will get this. If you calculate, you get this value. Okay. When for the VLTP, so this is VUTP. So may I write down something? So VUTP V out is equal to V plus saturation. For the VLTP, V out equal to the negative V saturation. Okay, so this is VLTP. Okay, where you replace with negative 10 volt, so you will get negative 4.67 volt. Okay, so this is the output for the VUTP and VLTP. So the question asks you to draw the transfer curve. Okay, so draw a transfer curve. So draw transfer curve is like this. So this is transfer characteristic. So we have to put the V output saturation, negative V output saturation, VLTP and VUTP like this. So you have this one 10 volt, okay, for the V saturation, plus V saturation, negative V saturation, negative 10 volt. And this one is your VUTP. And this is VLTP. Okay, so this is your transfer characteristic curve. Okay, but the question asks you another thing, which is sketch the output waveform. So how to sketch the output waveform? It is the same thing like in the comparator just now, okay, where you have to compare the condition. Okay, I need to copy. Let's do it together. Okay, now, so that would leave anything. All right. Okay, so with this, the same condition, okay, where V input, blah, 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 the same condition like that, okay. Okay, so this is the first condition. This is the second condition, okay. All right, okay. So now, okay, you have two conditions. Instead of you have one, in the previous one, you have one condition only, where you have one line only. For example, in this case, you have one line only, which is V reference there equal to V plus, or V reference equal to Vm over 2. So now you have two lines, okay, which is at V LTP and VUTP. So you need to apply the same condition, okay, but you have two lines, okay. One line here, VUTP, okay. One line here, VLTP. Okay, so let's take a look here. Okay, so you have, okay, look at here again. Okay, your VLTP and VUTP is V plus or V minus?
TP V plus.
V plus, okay. VLTP and VUTP is V plus. So you have here, so this is the line, oops, sorry. Okay, so this is the line for V plus. Okay, all right. Okay, so now, so V minus, so where is your V minus? Who is your V minus? V minus equal to? Hello? V minus equal to?
V in.
Yes, V in. Okay, V minus equal to V in. Okay, so I want to take one point. So this is V in, which is equal to the V minus. So I want to take this point here. Okay, this point. Okay, let's try this point. So in this case, V in greater than the V minus, V minus greater than the V plus, or V plus greater than the V minus. The yellow region there. Someone?
V minus.
V minus
Greater.
greater than the V plus. So V minus greater than the V plus, is it first condition or second condition? Second condition, right? So in this case, V out is equal to the negative V saturation. That's why you have it here. Here is the line of the output. Okay. All right. Okay. So let's take a look over here. Okay. So you have the line over here. Okay. So this is the line. Okay. I use different color. So this is the line. Okay, so you have the region here, this region. So can someone tell me about this condition? Can someone tell me the condition for this one? So your V minus less or greater than the V plus, this condition. So yellow is V minus. Okay. The line for VUTP is V plus. Therefore, it is greater or less.
Less.
Less than the V plus. Okay. So it is the first condition, which is V out equal to this one. Okay. V out equal to plus V saturation. That's why you got it here plus. Okay. And so on. You have to draw continuously the line there. Can you do it your own? Okay. One by one. Is it okay? Hello?
Yes, Doctor.
Yes.
Yes, great. Okay, thank you everyone. Okay, so I think that's it for the um, Smith trigger and also comparator. Okay, I hope you try this. Okay, I have time maybe like 10 minutes. Okay, can you try this on your own? Next class, I'll go back to the answer. Okay, I hope you try it. Just drawing and compare the condition. Okay, you need to do it yourself, because if you didn't do, okay, you will not be familiarized with the condition and you will get confused. Okay, once you do, you make an attempt to draw it, you will be familiar with the condition and you will be fast in drawing the waveform. Okay, so I leave that one to all of you, but I want to go back to this one. Okay, the last stop we have here. Okay, because I have time like 10 minutes. Okay, all right. Did you manage to get the answer for this one? All? Have you all tried? Okay, all right. So for the op-amp one, okay, I think some of you have tried because you messaged me. I got message, okay, from some of you, but let's give a try here, okay. So now you have op-amp 1, op-amp 2, op-amp 3, and op-amp 4. For op-amp 1, okay, it is obviously op-amp 1 is the inverting amplifier. Okay, why? Because negative connected to the input. Okay, op-amp 2 is the unity follower. Okay, op-amp 3, it is equal to what? Op-amp 3, someone? Op-amp 3, non-inverting amplifier. Are you all there?
Yes, Doctor.
Right, non-inverting amplifier. Okay, op-amp 4, op-amp 4, what is op-amp 4?
Inverting summing.
Yes, summing amplifier, correct. Oh my God. Okay, number 5, also this is inverting. This is non-inverting. Okay, all right. Okay, so for op-amp 1, okay, you need to find the V out 1. So for op-amp 1, V out 1 here, since this is inverting, therefore you have the equation, it is negative 2K. Okay, you can refer again, over 1K times the input 2 volt. Therefore, V out 1 here, you will get negative 4 volt. Okay, this is negative 4 volt. Okay, did you get the answer? Negative 4 volt for the V out 1?
Yes.
Okay,
Yes.
yes, great. Yes, great. Okay, so for the input 2, it is unity follower, which is quite straightforward. Therefore, V out 2 is equal to
2 volt.
2 volt. Yes, correct. Okay. For the non-inverting amplifier, okay, for the non-inverting amplifier, so you have V out 3 here is equal to the 1. Oops. Okay, 1 plus the same resistor there, 1K over 1K, all right, times 2. Okay, is equal to 4 volt. Okay, 4 volt. Okay, just a simple question. What happened to this 0.5K? Why we didn't take it into consideration? What happened to this 0.5K?
Short.
Yes, correct. It is short circuit. Why short circuit? The current here? Positive.
0.
Yes, 0. Correct. So it is this short circuit? Ish. Sorry. Terkeluar pula. 0. So this is short. Okay. All right. So next up, OPAMP4. Okay, OPAMP4 is summing. So I put it here as OPAMP4. Okay, summing amplifier. So you have the summing. You have this input here, 1, 2, and 3. Wow. Okay. All right. So you have 3 input over there. Okay. Therefore, for the V out 1, you have, since it is V out 4, since it is inverting, therefore it is equal to negative 2K over negative 4. The first one over 2K. Plus 2 over 2K. Okay. Plus 4 over 2K. Right? So you get V out 4 negative 2 volt. Okay, negative 2 volt. Right? Okay, so V out 4 is summing amplifier with 3 inputs. Okay, negative 4 volt, 2 volt, and 4 volt. Okay, so you have that one, 2 volt. Now, for the OPAMP 5,
Doctor, about
yes.
the OM5 is different amplifier.
The OPAMP 5 is, wait, is it different? Not summing, Mm, yes, correct. It is different amplifier. Okay, it is different amplifier, not summing. Yes, thank you. I also, okay, I need to open one more slide, okay, so that easier for me to find the OPAMP 5. Okay, one more slide here. If you notice, I didn't upload yet the slide after for the OPAMP. I will upload after this, after I discuss this. Okay, so let's take a look here. Okay, so how do you solve the OPAMP 5? Okay, so OPAMP 5 is easy. Okay, you can solve it using, if you don't know, okay, for example, you don't know how to solve it, difference amplifier, okay? So you can always apply what? Okay, for the OPAMP 5, you can always apply total current. Oh, total current in is equal to the total current out. You can always apply this, okay? So in this case, you have current, okay? For example, I take different color here. So I take this as I1, okay? And then I take this as I feedback, okay? And then this is I2. Okay, so you can solve that one, okay? Means that you solve, since you know the current here, I minus equal to 0, okay? So you can solve KVL or KCL at that node. Okay, so if we solve, okay, if we solve KCL at node V minus, okay, for example, so you have current in equal to the current out. Okay, so what is current in over here? What is it? Kejap I did. Alah, no current in. Okay, so you have current in. One more time. Let me draw again. Okay, so this is different color. I1, I feedback. Okay, and then you have here I2, and then you know that current here I minus equal to 0. Okay, so current in to this node is I1 plus I2. Am I right? Also plus IF. Am I right?
Yes.
Yes. Okay, so in this case you have I1 plus I2 plus IF equal to 0. Okay, or equal to the I minus, which is 0. Okay, so you know that I1 is the current to the right. So I just take that I1, okay, is equal to the, so V out 4 is 2 negative 2. Okay, negative 2 minus 2 over 1k. Okay, plus I2. I2 is 6 minus 2 over 2k. Oh my god. 6 minus 2 over 2k. Okay, while I feedback is equal to from V out 5 minus 2 volt over 2k. Okay, so in here you will get negative 8 plus 4 plus V out 5 minus 2 equal to 0, and it is equal to V out 5 equal to 6 volt. Okay, you can derive like this, or you can also apply the derivation from here where V out equal to the V1 minus V2. Okay, this V1 minus V2. Okay, times R2 over R1. Okay, which is the same circuit like here. So this is different amplifier. Okay, so you will get the same answer, 6 volt. Okay, if you don't know, you can always, okay, remember, we have derived everything for the inverting, non-inverting, everything. But if you get lost, I mean, you forgot everything, just remember, you apply KCL. Okay, whatever node you apply KCL. For example, for the OPAMP 1 here, okay, so you lost with this what type and you lost the idea how to solve it, just you apply KCL. Okay, apply KCL, because if you look at the derivation at the back, all is about KCL derivation. Okay, all?
Doctor, why
Yes.
using minus 2 like? Minus 2, minus 2.
Again, one more
Uh,
time.
about the last question.
Mm-hmm.
Yes, this question.
Mm-hmm.
The I1 is
I1.
minus 2, minus 2. The back one minus 2 is come from where?
The back one, V out 4 is minus 2. So
Yeah.
the front one is minus 2. Oh, okay. So you solve this node. Okay, I didn't show it here. Okay, you solve this node. Okay, you will get this node V plus equal to minus 2. And V plus is equal to the V minus, kan? Right? So you need to solve
Oh,
this
yes,
node
yes.
with V. Okay, you got my point? solve the V
yes,
plus.
yes.
Yes. Okay, solve the V plus. Okay, solve V plus. Okay, you will get -2. So if you take condition V plus equal to the V minus, therefore it is equal to the -2 volt as well. Okay, all right. Do you know how to solve V plus? Of course you know. Solve V plus using another KCL at node V plus. All right, all students. Hello.
Yes,
Okay.
doctor.
All right. Okay. I think that's all for today. We finish early. I need to catch up another thing at supposed to be 12:15, but now 12:20. Okay. I think that's all for today. Also, see you in the next class. We will discuss on the tutorial multi-stage amplifier, as well as we continue a bit on the Smith trigger just now. All right. Okay, all. That's all for today. Thank you all. Bye.